Okay, good morning all of you once again. Let me commence in today's class with module 1 of analog electronics. Okay. This is a study material which I am going to upload in the Google Classroom. Everybody can download from there. If you look at module 1, I just will show you the syllabus what we are discussing. Okay. This is more detailed syllabus of VTU. So, particularly I will move to analog circuits to give an overview which module we are commencing. Last class we discussed about the subject code, CIE marks and the course objectives also. Briefly I have introduced what all the things we are going to discuss in each and every module. Module 1 seems to be little bit of lengthy because so many things we need to cover in module 1 related to BJT and as well as MOSFETs. Module 2 particularly talks about MOSFET amplifier configuration and its related things. Module 3 which talks about feedback amplifiers and power amplifiers. 4 is purely on op amp with negative feedback and general applications. Module 5 talks about op amp circuits only. Last class we also told about course outcomes. There are totally 5 course outcomes here. Students will be able to understand the characteristics of bipolar junction transistor and field effect transistors. Okay, so these characteristics you will be in a position to understand, and once you better understand these two devices, so then it will be easy for you to study the circuits, or analysis of circuit becomes very easier. Okay. And next is design and analyze BJT and FET amplifier circuits. Two things we need to focus here, one is design aspects and as well as analyze aspects here. Design means you should find out for a given input and output what should be the BJT resistance, capacitance, all those things we need to discuss here. That is a design aspect here. First we will do theoretical design, and once we are through with that, then we can go for circuit analysis. Okay, here we will take two fundamental device and rig up the amplifiers. One is BJT and other one is FET. Okay, so these two devices we are going to use in the amplifier circuit design. And when it comes to oscillator, again there is one more outcome here. We need to design sinusoidal and non-sinusoidal oscillators. Here analysis part is not given, just we design and we stop at that point itself. And next outcome is we will be in a position to understand the function of linear ICs such as op amp. The best example for linear IC is operational amplifier here. In this outcome here, we will try to understand the function of linear integrated circuit, particularly the op amp, and later we will focus on the circuit design related to the op amp. Okay. We will start with the simple circuit design and move on to the complex circuits. Okay, I do not want to go deeper into the question paper pattern since we have discussed this in the last class. Textbook is microelectronic circuits. You can also refer to lower editions instead of 6th edition, because I feel that lower editions are much more better, though the advanced topics has been added into this 6th edition, but I also suggest you can access this copy from the library. 4th and 5th also seems to be good. Okay, you can refer to the any one of those editions, 4th or 5th. 90% of syllabus is covered in this textbook itself. Okay, this is very good book in my opinion. Lot of details are there in this book. Okay, and students who are unable to come to college, you can download this book from the internet also, browse and you can download this book from online. Okay. Even this second book which is specifically for operational amplifier. So, this is also a good book, which you can students can refer for op amp. Okay. Reference books, is up to you. You can for additional information. Sometimes if you feel difficult to understand from the original or prescribed textbook, students also can refer these 3 reference books are mentioned here. So, all 3 you can keep it with you, but whenever circumstance comes, you can refer to that. Now, with this syllabus background, I will just move on to the today's topic. Let me start with module 1. As per the syllabus, you know that module 1 is which talks about both BJT biasing and MOSFET biasing. Okay. So, that we will start here. Okay. So, let us look into the highlight. So, you can see BJT biasing. Okay. So, BJT biasing is nothing but which is an important design in the amplifier. A preliminary part in the amplifier design is the BJT biasing. We should set the voltages and currents within the biasing circuit. We will take sample biasing circuit and explain that how exactly biasing circuit looks like, and what parameters you need to pay an importance. Those things we will discuss. Biasing is a BJT amplifier circuit. It is a sub circuit of this amplifier circuit. The very old method is this classical discrete circuit, which is very popular, is voltage divider bias. And there is another type of bias which is also important, is collector to base feedback resistor. We will discuss these 2 bias circuits in more detail with advantages and disadvantages of these 2 things. Next highlight of this module 1 is going to be small signal operation and models. Here we will discuss the output current, which is particularly the collector current. What is the magnitude of collector current flowing in the output of a circuit. When it comes to BJT based amplifier circuit, we discuss on the collector current. When it is MOSFET, we talk about drain current here. Okay. And the transconductance also an important parameter of the MOSFET, that also we will discuss here. Base current, input resistance, emitter current, input resistance, voltage gain, and these are the important parameters of the amplifier circuit here. And also we need to understand how to separate AC quantities from the DC quantities. Okay. So, when we say AC quantities, the capacitors comes into play. When it is a DC quantity, we will remove those AC elements such as capacitor, and the circuit is purely the DC voltage and with BJT and resistances here. And we will also discuss the hybrid pi model. Okay, that is an important thing here. These are the things which these first 2 points highlights on BJT, and the second, third and the fourth point highlights on the MOSFET here. The things what we have discussed in BJT is the same things also will be covered in MOSFETs here. We will start with the biasing in MOS amplifier circuits. Here we have 3 types of biasing, just similar to the BJT. Fixing VGS, we will see by fixing gate to source voltage how we can maintain constant output current. We will see that, and once we discuss this with the voltages and currents, we will see whether this can be used as a bias circuit in the amplifier or not. We will see that after discussing the merits and demerits of this fixed VGS gate to source voltage. Another way to maintain output current constant for variations in the temperature or the parameter change, the output current should be constant in an amplifier. How do we maintain output current constant in an amplifier? The one way we already said, it is by fixing gate to source voltage. Another way is by fixing just gate voltage. We will see this mechanism, how this is better than the fixing gate to source voltage. We will see that when we study the more details of this circuit. Another circuit which is also very popular is by providing a feedback in the MOSFET, that is from drain to drain is the output terminal of a MOSFET. MOSFET looks something like this, Okay. So, this is a structure of a MOSFET. We have a gate here and drain here and source here. Look at this type of feedback is we are connecting drain back to the gate. So, that means we will use some resistance here and take the output here and connect back to the input here. So, this is a feedback resistor here. A signal current flows like this here to the gate of a transistor here. The voltage whatever establishes here that provides a feedback to this transistor here. So, such kind of biasing circuit is called as drain to gate feedback resistor based biasing here. So, in from examination point of view, this three circuits you need to remember with advantages and disadvantages. To proceed further, we have a small signal operation and modeling of this MOSFET amplifier. So, we will discuss what is DC bias points, signal current in drain, voltage gain, small signal equivalent circuit models, transconductance. Though we discuss here transconductance with reference to the BJT, it is more important with reference to the MOSFET. Okay. So, here we have something called as a beta 1 by beta, that is called the transconductance. Transconductance is actually the measured in terms of a gain. Same here, it is current by voltage in case of MOSFET, that is called as a transconductance. Okay. So, these are the important highlights of module 1. Now, let me proceed directly into the BJT biasing. Let us introduce here. The first point, if you see here, the amplifier is the main component of any analog circuit. You take up any analog circuits, okay, so maybe the circuit which is very important from different application point of view. In all those things, the amplifier serves as a fundamental block here. Even if you look at an op amp, in that you can see that it is a linear IC moreover, and in that it linearly amplifies the input signal. It is an IC version of an the amplifier, but here what we are talking is a discrete version of an amplifier. So, for any analog circuit, okay, it may be the PLL, it may be the oscillator, you take up any analog circuit. In that the main component is going to be the amplifier here. It is not only because of they can amplify a signal, but they can be configured into many other useful circuits with a proper feedback. You will see that in oscillator circuit, by just providing a proper feedback from output to the input, and you have to ensure that the phase between the output and input. Okay, so, proper phase if it is established, definitely the circuit amplifier circuit can work like an oscillator. Okay, so, here I want to stress here for any analog circuit, the amplifiers plays a significant role, and by just modifying this amplifier we can build variety of circuits here. That is what the first point we will talk about here. Now, more detail if you look at the amplifier, what it is exactly doing. Let us look at from the transfer function point of view. So, if I consider a linear amplifier, many times we expect the amplifier to be linear. Even non-linear amplifiers are used in some applications also, that we will discuss in coming classes. But just observe an input output function, that is called as a transfer function of a linear amplifier, which looks like something like this. V naught is equal to AV times Vi. So, V naught is nothing but this is the output voltage of an linear amplifier, okay, and AV is nothing but it is a voltage gain, and Vi is nothing but it is an input signal here. So, AV is the amplifier gain, it is a transfer function plot, and it is a straight line that goes through the origin something like this. It is a straight line that goes through the origin something like this. Okay, so, this is the linear function. Okay, it is a transfer function, it is which is a straight line that goes through the origin, that is what it is written here. And now we can show the Vi along x axis, and we can plot V naught along y axis here. The curve between V naught to Vi is going to be a linear here. Such kind of amplifiers are called as linear amplifiers here. Any amplifier that exhibits this kind of the transfer function. Okay, so, this is a transfer function. Okay, so, that kind of amplifiers are called as linear amplifiers here. Okay, so, AV can be negative, indicating that there is a 180 degree phase shift in the output. The gain, sometimes we may get output voltage something like this, V naught is equal to minus AV times VI. Okay, so VI you can see here. So, this minus indicates there is a 180-degree phase shift here between the input and output here. That means, if you have a amplifier circuit something like this, okay. So, if it is an amplifier circuit and when we apply input signal here, so let us indicate this as output signal here and this is going to be the input signal here. The negative sign here shows if you apply here sinusoidal with the positive going to negative going something like this, it will be inverse here. That is what the 180-degree phase shift indicates here. Okay, so it is going to be a small signal. Okay, maybe the magnitude is 50 millivolt, and here you get in terms of volt. Maybe the positive peak is going to be 0.5 and the minus 0.5. Totally it will be 1 volt peak to peak. Okay, that is how the signal will get amplified. Okay. So, here if we want to stress here the 180-degree phase shift, minus sign indicates there is a 180-degree phase shift here. Okay. Any questions so far?
No, sir.
Okay.
No, sir.
Okay. Okay. So far we have seen that the transfer function seems to be like a linear, but generally if you look at BJT based amplifier circuit, the transfer function, for example, if you consider the common emitter amplifier circuit which is shown here, the transfer function for this may not be linear. Let us show the curve here. Look at this transfer function. Okay, this is the transfer function. If you plot a graph of V naught versus Vi, it is going to be a non-linear here. Okay, so you can see it is a straight line here, which is perfectly horizontal to the x-axis, parallel to the x-axis, and even for higher voltage of input, you can see it is again very close to the input signal. And if you look at here, the overall signal is going to be a non-linear kind of the transfer function here. Okay. So, now question is how do you use this in a linear amplification here? Now, we should look at a piecewise linear part in this curve here. That means, overall curve may not be linear, but some portion of this curve is linear. You can see from here till here it something looks like a linear curve like this. Okay, so it is linear curve like this. Okay, so any input signal given here, okay, it will be amplified in a linear manner here. Okay, so the curve looks like here. This curve, even though if I zoom it this, it will be something like this. Okay, that means overall the circuit behavior is non-linear, but at some portion we have a linear characteristics. And now if you bias this, this is the input signal, this is what you are seeing in the bottom here, and this is very small signal, and you can see there is a negative portion and a positive portion here, and this is sinusoidal signal, maybe the magnitude is a few millivolts here, and if this is biased to this center point which is operating here, bias in the sense you maintain DC voltage such that the signal level from the origin it is pushed, or it is levels are raised till here. So, this can be done by DC biasing. Okay. Because now this is an AC signal. AC signal, if you do not bias, what happens, this will be at the origin, and negative portions are suppressed and positive portions are passed. But now we want both positive portion here, what you are seeing in the output, as well as negative portion here. To retain both positive and negative portion, we need to bias. Biasing means adding DC to the circuit. Once we do that, the AC signal will be elevated such that the bias should be applied such that it should be at the operating point here. So, now you can see that now this when AC signal is made to swing at the operating point, now you will get a linearly amplified output, okay, like this here. So, the both negative swing and positive swings are retained here. Okay, this does not happen without biasing here. So, we must apply biasing, so that signal will be the circuit adds DC to the waveform. This sinusoidal which is earlier, it will be oscillating at the origin, Now, this is pushed into the linear region is till here to here, it is a linear region, and the signal will be faithfully amplified here. Okay. That is how the things work in a linear amplifier. So, we have conveyed that here, you can see here. As we can see from the transfer function presented in figure 1.2, this is the figure 1.2, this is curve transfer function of this circuit whatever we have shown. Transfer function is nothing but it is a graph of V naught versus Vi. Okay, so, that is the transfer function. If you plot practical characteristics, you will get a transfer function something like this. So, we are not interested in plotting the transfer function of the circuit here, but our intention is to explain how amplifier behaves when the device is exhibiting non-linear kind of transfer function here. Okay. So, from figure 1.2 it is non-linear. So, by looking at this curve, we can say that the curve is the entire input and output characteristics is non-linear. Linear means we expect at least a 45-degree line something like this, that is a linear, but overall the curve is non-linear, but at some portion there is a linearity exists, that is called piecewise linear. Okay. Piecewise, if you split this curve into small portions here, at one particular piece of this curve the linearity exists here, that linearity can be used for amplification purpose. Now, here the same thing we have explained here. For example, if you apply signal like this is cosine signal we have considered here, sine or cosine there is no much difference. Here we take as a cosine signal as a input signal. Okay. So, this is Vi is equal to Vi is nothing but this is an input and is an positive portion or amplitude cos omega t, this is the frequency component here. So, Vi is equal to Vi cos omega t, this is the input signal that is applied to the BJT, and V naught will be equal to VCC for all input signals lying less than 0.5 volts. Just observe this one here. Okay. So, any signal, even though we apply here the this cosine signal here, cosine or sine, only the phase is going to be difference, this is going to be the cosine signal I can see here. So, when you apply this kind of signal for this circuit, what will happen here? So, you can see here, observe here from 0 to 0.5, okay, the input signal is suppressed and output will be the VCC. Are you seeing here? So, this is our input signal is taken along x axis here. This is the input signal which is taken along x axis, and just observe in this range, when input is lying between 0 to 0.5, and you can see output is, this is output along y axis. Okay. Output is VCC. VCC means it is just high voltage 5 volts. That means output remains at 5 volts. This we are showing on the characteristics. Now, let us look into the circuit and see same thing here. This is the input signal. Okay. So, we are applying here a cosine signal as an input. Vi is equal to let me write here. So, this is Vi cos omega t, that is the input we apply, which we apply here. Okay. Now, see what happens here now when the cosine signal is applied here. Okay. So, now here when the input is lying between 0 to 0.5, why 0 to 0.5, 0 volts to 0.5, output remains at 5 volts here. Any idea? When input is lying between, since it is sinusoidal here, okay, sinusoidal signal what we apply here, output remains at VCC. Okay. For input lying between here, the input is lying in this range 0 to 0.5 volts. Any idea here why the output is at VCC, or if I assume this is going to be 5 volts, output also will be at 5 volts. Okay. Any idea here? Let us look at the working of this circuit. We know that minimum voltage is VBE for the transistor of silicon is going to be 0.7, okay, but 0.5 onwards this will start conducting, but look at here the condition here is the cosine signal cos signal is applied between 0 to 0.5. Suppose if this is going to be a sinusoidal here or cosine, this level is say 0.5 and this is 0. I am asking you what will happen to this range here 0 to 0.5 of input signal. Okay. Look at this now. So, 0 to 0.5 we know that transistor will be in off condition, transistor does not conduct, okay, because it is less than VB, right. VB for this transistor is going to be typically 0.7 volts or 0.5 to 0.7, it varies. For some transistor it may be the 0.5, okay, we have to see the manufacturer data sheet, and for some transistor it will be 0.7 here. Now, let us take it as a 0.5 here, 0 to 0.5, since between 0 to 0.5 transistor remains in the half condition. When transistor is off, you can see that here between this point to ground it remains as a open circuit, it is a open switch, something like this, okay, from here to here. So, here we have a ground here and this point is nothing but C here, okay. So, now what happens for this? So, obviously if you measure apply KVL here, okay, so minus 5 plus IC times RC, okay, this current will not flow because I do not have any, okay, the loop is not closed, right, okay. So, straight away this V naught will remain as VCC itself here, okay. So, current will not flow from supply to ground here, okay. So, there is no current flow here because this itself is open circuit here, the IC will be 0 here. So, therefore, this V naught will be equal to VCC, the voltage between this point and the ground will be same as the voltage between this point and this point. So, here we have VCC and same thing we will have here also VCC here. So, output remains at VCC here. So, this is what the conclusion from this here, okay. So, same thing is also shown here in the characteristics, transfer characteristics. So, between 0 to 0.5 you can see that output remains at 5 volts here, but look at a slight increase in input voltage, what is happening here. So, you can see that here we are entering this mode is called cutoff mode. Cutoff mode means transistor remains in off. So, you can write here this is in this region BJT is off, and you can see here the BJT is on here and here also it is on. The question here is when it is on here which mode it is operating, that is also very important here. So, here when the BJT just becomes on it will be operating in the active mode, okay. And if you increase the input signal beyond the base to emitter voltage, BJT enters into the saturation mode, okay. For amplification what is required is only active mode, okay. So, this region whatever it is shown between two parallel lines here, okay, this line here you can see here, this line here, okay. This region we can use BJT as an amplifier, this can be used as amplifier, okay. Whereas, in the cutoff BJT can be used as a half switch, and in the saturation mode BJT can be used as a on switch, okay. But in the active mode BJT can be used as an amplifier now. It all depends on now the bias circuit here, that is why our first module mainly focuses on the biasing, because now when I say biasing, that means we have some circuit which operates our transistor in the active mode, okay. If transistor operates here or operates here, it cannot be used as an amplifier, okay. So, only when the transistor operates here in this active mode, okay. So, that means your input signal must be greater than the VBE, I mean the cut in voltage of this transistor, and it should not be in the saturation, just it should be within the before the commencement of saturation and after the cutoff. So, between these two lines, parallel lines what you see here BJT can be used as an amplifier, okay. So, same thing is illustrated here, you can see, you can go through this, and as I said here, we are applying a cosine signal here to the BJT. So, V naught will be equal to VCC for all the input signal applied less than 0.5 volts. We note, however, that the BJT transfer function in the active region is approximately linear. Okay. So, it may not be perfectly linear, but approximately it is a linear, that is a straight line, although the transfer function is not going through the origin. That is also observation, you can make it in the characteristics. Here transfer function is not going through the origin, it in this region, in the active region, to some extent it is going to be linear. It may not be perfect, and this transfer function is in the active region is also not going through the origin. That is also an observation what you can make here. This approximate linear behavior can be utilized to build transistor amplifiers. As I told you, in the active mode we are using transistor as an amplifier here. To see this, let us assume that we add a DC component to the input signal such that BJT remains in the active region at all times. By adding DC component through proper the resistance and resistance selection and proper DC voltage, we can operate BJT in the active region here. Okay. So, VB is added to the signal of this is nothing but the input AC signal that gets that is equivalent to the Vi, which is sine wave in our case. Okay. So, that this input signal gets added with the DC signal here. So, VB is nothing but it is the inbuilt of a transistor. As I told you, VBE is a DC which is going to be around 0.5 let us say, and the AC signal is going to be around it is a cosine signal, this is a variable, okay, which gets added to this DC signal here. So, let me show here, this is, look, I can observe here we indicate AC signal with small b small e, okay. This is AC, this is DC, this is AC. Okay. So, overall input signal, if you observe here, overall input signal, let us write like this. Okay, small v capital I is nothing but VBE plus VBE, DC plus AC. So, this is an AC component, this is the DC component. Okay. Here we need to understand here why we are adding DC to the AC. So, by adding DC signal to the AC input signal, we are uplifting the AC signal to the active region. Okay, that is one important thing here. Okay, so, input voltage to the BJT circuit is same thing as shown here, you can see here. So, I will little bit zoom it so that you can observe correctly. Okay, so, you can see here now input signal Vi is nothing but VBE small v capital B is nothing but DC base emitter voltage and AC base emitter voltage. Okay. You can see here this is the total base emitter voltage. It can also be written as small v capital I, okay, and so that is the input signal, and you can see the corresponding output signal can be taken from at the collector point here. So, that we will discuss next year. Okay. A few more things which I want to bring it to your notice is see the input voltage and current notations, though we have discussed in last semester, DC quantities are written like this. So, for example, if it is a base emitter voltage, we indicate DC base emitter voltage with both V uppercase, base emitter also it is going to be uppercase. Okay. So, next is say collector emitter voltage, we indicate VCE collector emitter voltage. Okay. And there is another voltage which is VCC, which we indicate this is a DC. All these are DC, VBE, VCE, then what else we come across, any other voltages, DC voltages. I think these are the two voltages which are very important with reference to BJT. Same thing if you want to write this quantities for AC voltages, small v, small b, small e. Okay, everybody has to follow this notation to indicate the DC quantities and AC quantities. The moment you write this, we will think it is an AC base emitter voltage, and AC collector emitter voltage, AC. Okay, we do not have any such VCC here. Okay, remove this one, only we have these two quantities here. Now let us move on to the currents here. So these are the DC voltages. Let us see the currents here. We have three currents here. One is base current, DC base current, DC emitter current, DC collector current. Whereas AC base current is denoted as small I, small b, small I, small e. AC emitter current, small I, small c is AC collector current. Okay. And total current here, total voltage or total current. Let us see how this can be written here. Total voltage or current. How can we denote that in an amplifier circuit? So, total voltage, suppose if it is a VBE, we will write it as small v capital B. This is a total base emitter voltage, which is sum of this plus this is equal to this. Similarly, collector emitter voltage can be written like this, small v capital C E. So, sum of this DC collector emitter voltage and AC collector emitter voltage can be written like this. Okay. And this is VCC. VCC we have only one quantity. This is the input. Just remove this. This is VCC. Okay. Now, when it comes to base current, total base current here, we can write this as small I capital B, which is again this plus this. Okay. This plus this, totally it is IB base current here. Similarly, we can write total emitter current, total collector current here. Okay. So, these are the notations which you need to be familiar, especially in module in this entire course here. Okay. Any questions about this notations?
No.
Now, can you label it here? Can you see what quantity is this which I am highlighting?
Total collector emitter voltage.
Yes, it is total collector emitter voltage. Okay, total collector emitter voltage. So, immediately we can see, understand, see total base emitter voltage. Look at this, total collector emitter voltage. Okay, I am seeing why this comes always. Let me zoom it. This so much of notifications. Okay. Right. So, hope you understand the notations here. Look at here now. This is total base emitter voltage, and you can also see that here this is total output voltage, total collector emitter voltage. This is total collector current. This includes both AC and DC. Okay. Okay. That is how the interpretations are done here. Okay. All right, let us move to the next thing here. I think we expand this total base emitter voltage, how it is sum of both this. Now, we can find the response of the BJT to this input signal. So, here we have discussed input signal, total input signal, which includes both DC and as well as this is the DC quantity, and the second part what you see is, since you can see here both are small, it is an AC quantity here. So, having applied this kind of input signal to the BJT here, okay, so which includes both AC and DC, what this transistor will do? Let us assume that this transistor is operating in the active region. Okay, now, what it will do? It will do linear amplification, right. As per this characteristics you can see here, where if you are operating here and if you apply both DC to elevate this AC signal to the active region, and now once this is sinusoidal signal is applied in the linear region or active region, the transistor amplifies that to the maximum extent, and you can see the amplified signal here. Okay, that will show while explaining this output voltage. So, in response to the BJT for the input signal that we have applied, this is the input signal what we have applied, Vi is equal to capital VBE plus small VBE. With reference to that, the signal will produce the output utilizing the BJT transfer function here. At any given time we can find the input voltage VBE. Okay, VBE is nothing but it is a total base emitter voltage, that is VBE versus time axis we can also plot. You are seeing here the same curve VBE versus time. You can see here this is, though it is shown vertically downwards, here you can see this is our axis. If you look at this graph, this is VBE, not VBE, it is small VBE, let me, so this is total base emitter voltage. So, small v capital BE, you can see here this is sinusoidal signal which is plotted with reference to the time axis. If you see this as a distinct signal that is applied as an input here. Now, this signal, input signal, when it is operated in the device which is operating, when it is applied to the device which is operating in the active region. Okay, so, the signal will be amplified by the gain times here. Every device will have its gain. In case of BJT, we have, since it is operated in common emitter configuration, beta is the transistor gain. So, that much times the signal gets the elevated or boosted. Okay, so, that is what it is told. This is VB versus time also we can plot, use the transfer function to find related VC for that time. We repeat this procedure at different times and construct a plot of VC versus the function of time. What we are trying to say here is, okay, for every signal whatever you see here with reference to time, VBE, total base emitter voltage with reference to time, this corresponding the, for example, you can see a negative peak comes here, this is a negative peak here, and look at here negative peak has become positive peak here. Okay, and look at here the positive peak of input signal is here, and look at here again this is now elevated, this is extended to the transfer characteristics here, and if you draw the horizontal line here, and you can see here there is a negative peak here. That means this positive peak, negative peak of input signal has become positive in the output, positive peak of input signal has become negative in the output, because of there is a 180-degree phase shift between the input and output here. Similarly, negative here is a positive here, and positive here is a negative here. Okay, so, that means you can easily take an input signal and superimpose this extreme points onto the transfer characteristics, and corresponding horizontal lines can be drawn here. Now, this time axis here you can see here this is vertically downwards here, this when it is exactly at the midpoint, this can be written as horizontal line here. Okay, and that you can see that here the signal is going downwards, and look at here at the output, when it is going downwards, here it goes out upward. Okay, because the gain is negative. Okay, and negative signal going becomes a positive, right, because earlier we discussed transfer function, right. What is the transfer function of this circuit? We said it is V naught is equal to minus AV times, okay, Vi, this is the transfer function, right. In our case this Vi is nothing but which is Vi times cos omega t, this is the input signal, and now look at here this cos is going negative, but transfer function is also negative, negative of negative becomes a positive here. So, that means when signal is moving, this is our 0 line, middle line, going less than 0, and here it goes above 0. Okay. When it goes to more negative peak, this will be at positive peak, and again signal is coming from negative peak to the 0 crossing, this is 0 crossing. So, now you can see that again the signal comes from positive peak in the output to the 0 crossing. Okay. And 0 crossing of this input sinusoidal and the output sinusoidal are same, and again signal goes positive here and attains positive peak. Look at here what happens to the output signal. When signal is input signal is going positive, output goes negative, cos is negative. When cos negative, overall output becomes positive. When cos is positive, the output becomes negative. So, output is going negative like this, and it goes to negative peak, and again this kind of excursion will happen. And let me ask a question here, why the peak to peak value here is small and peak to peak value here is larger, because this is amplified by the beta times. The input signal is amplified beta times the input signal makes the output signal here. Okay. So, that is how the things can be interpreted with reference to this amplifier. Okay. The transfer, this is the transfer characteristics, and we are showing here both input signal and as well as the output signal here. Okay. So, the resulting output signal is superimposed on the DC collector voltage VCE, and what you are seeing here is purely the AC signal here. When you look at from circuit point of view, here the output signal has got both two components. One is AC collector current VC small c plus DC collector current, DC collector voltage here, not current here. So, this output just remove this is only for specific level, we told it is output is equal to VCC, but generally for input cosine signal, what is the output? When we apply AC plus DC, output also will have both AC and DC. So, now here V naught will be equal to AC signal plus VC, V naught is equal to, okay, so VCE plus DC VCE. Okay. So, this is AC output signal and this is a DC output signal. Ultimately, we want AC output signal. Okay. So, this we can retain it, and this will be there in the circuit, this DC is not required for us. So, the amplified signal will be a shifted version of the AC, okay, because of this DC signal here. Okay. So, that is what it is told here. V naught appears superimposed to the DC collector voltage VCE. The amplitude of V naught is larger than that of the VI by the voltage gain AB, because AB is the factor that gets multiplied with the input signal. Okay. So, I hope today's class we discussed about simple the amplifier circuit, which is a common emitter configuration circuit, and we discussed various AC quantities and DC quantities, and how the circuit amplifies. We have showed that with the help of transfer characteristics. Okay, and we also discussed about various modes of operation of BJT, cutoff mode, saturation and active mode. We also said that cutoff mode saturation can be used as a switch, active mode can be used as an amplifier, and specifically we have discussed voltage levels of each of this input and the corresponding output voltages we have shown with both AC and DC quantities here. So, next class we will discuss more about this continuation of this, and see notations already it is shown here. Okay. We will continue these amplifier circuits in the next class also. Okay. So, thank you all for watching today's class, and attendance can be marked in the this chat box.